Okay, well, now we'll look at the expected value of the hypergeometric random variable, which is defined this way. And you can use more general language. You don't have to talk about colored balls or anything like that. We'll do a problem with a deck of cards in a second. But this does describe it. So X is the number of, say, red balls that are selected when we pick N from a jar with capital N balls, but little m of them are red, or whatever feature we want of whatever thing we're picking. Okay, so n, we require little n to be less than or equal to the number of that feature, and that feature should be obviously less than or equal to n, capital N. That's sort of obvious. So yes, so we did an example like this with the queen before, right? Choosing the queen. So let's do this with the choosing the queen. So suppose we pick let's do an example of this, and then we'll say what it is. We'll pick two cards. So little n is 2. So little n equals 2 from deck of cards, of which, as usual, we'll do the queens, of which m equals 4 are queens. And we want to know, we'll let then x equal number of queens selected. We computed these probabilities from in a previous lecture. I think we got, yes, so from previous lecture, we found probability x equals 0 was 181, I think, over 221. Probability, I'm not sure, I'm going to check in a second. X equals 1 is I'm not sure this is right. Probability x equals 1, we'll probably do this. Probability x equals 0 is I pick no queens on the first one, so that's 12 out of 13. And then given, I chose no queens on the first one. So that all 4 queens are still in the deck, I have to pick 47 over 51 to get another no queens. So if I do this, what do I get? I get 4 times this. I get 160. I get 188. I think that's what I want here. So this is 188 over 221. Yes. Okay. So that's this one. Now, the probability I get exactly 1 is equal to 32 over 221. This comes from, I could pick none on the first, and then I pick one of the 4 on the second. Or I could go the other way, right? I could have 1/13, and then times the probability I don't pick 1 on the 48 over 51 here. So I get 48 and 48 over this, over 13 times 51. So that's, yes, this is right. And probability x equals 2. Well, there's only one way to do that over all of them. It would be 1 over 13 plus times 1 over 17. So this would be 1 over 221. And E of x which we found last time, was 32 plus 2 times 1, which gives me 34 over 221, which is 2/13. Now, 2/13 looks curious, right? It looks like 2 times 1 over 13. And this is what it is. So how do we show this? So the way to show it is, let's represent x as the sum of random variables. So we'll let x1, xi equal 1 or 0. This is if queen selected on draw I. If not a queen selected on draw I. Okay, so x1 is 1 if I pick a queen on the first one, and it's 0 if I don't pick a queen on the first one. Well, it's pretty clear then. A couple things are clear. First of all, x is equal to x1 plus x2. This is clear. If I pick one on the first and one on the second, then x is 2. If I pick one on the first and don't on the second, or I pick one on the second, not on the first, then it's 1. If I don't pick either, it's 0. So, EX, I don't even have to care about independence, is EX1 plus x2, and I use the proposition EX1 plus EX2. Now, what is EX1? EX1, probability I pick a queen on the first one, is equal to 1 over 13. Now, what's EX2? Well, we know from the answer it should be also 1 over 13. EX2 also is 1 over 13. Here's why. First of all, it's an unconditional probability. So if you think about it, there's no reason to suspect that that it's any different than the first one, that you would get a queen, because it's before the game starts. You're saying, what's the probability the second pick is a queen? So you would say it's the same as the first, same as the last. There's no favoritism. So that whole thinking goes, can show you the way to prove this too, because all it's saying is I want to consider all equally likely outcomes and consider which ones are queens. So if I do it that way, this is equal to, this is true since, true. Sorry, E of x1. The probability, I wanted this was E of x1. Yeah, it is 1/13, right? And this is 1/13. This is true because, right, this is equal to 1 times the probability x1 equals 1 plus the probability x1 equals 0 times 0. So this is 0. So this is 1/13. Same reason here, right? This is equal to 1 times. Okay, so this, and then plus 0, this is equal to 1/13. Here's why. Probability x2 equals 1 is just equal to the probability x2 equals 1 given x1 equals 1 times the probability x1 equals 1 plus probability x2 equals 1, x1 equals 0 times the probability x1 equals 0, right? It had to come from one of these. So this probability here is just, I can do this out. Probability x1 is 1. That I did pick a queen there is 1 out of 13th. Probability I pick a queen again would be 3 out of 51. Plus the probability I did not pick a queen, that's pretty good, 12 out of 13. And the probability I now pick one, given I didn't, would be 4 out of 51. So if I do this, I get, what do I get? 48, and 3 is 51, so I get 1 out of 13. So we did show that these are both 1 over 13. We could do this for any exk, like this. So ex equals ex1 plus ex2, 1 over 13 plus 1 over 13 equals 2 over 13. Note, this is true even with x1 and x2 dependent. Yeah, I'm scared I was running out of time. So we can show this by, let's just have the probability x1 equals 1 and x2 equals 1. This is equal to, well, it's a probability they're both 1. So remember, this was 1 over 221. But this is not equal to probability x1 equals 1 times probability x2 equals 1, which is just equal to 1 over 13th squared equals 1 over 169. So they are not independent. There's a lower chance x2 is 1. That's one way to think about it, if x1 is 1. So I get a smaller probability here that they both are, rather than that their product would be. Okay, there's some information here. If the first one is a queen, the deck is smaller, and this is not the case that these are equal. So, but we still get this result. We always get this result. Okay.